We have learnt about AC to DC converters, which are known as rectifiers, but I think it is good to know what kind of rectifiers are used in various applications typically. As we know, rectifier is a power electronic circuit which converts AC to DC, AC voltage to DC voltage, and the input voltage could be single phase or three phase AC, which is usually sinusoidal. In domestic applications it will be single phase AC, in industrial applications it will be three phase AC, and we have a DC voltage that is produced at the output. And how about the input voltage waveform? The input voltage waveforms are usually sinusoidal because they are directly from the utility, and we want an output voltage waveform which is like this ideally. And since it's a DC circuit, we will also have an output current ideally which is a constant like this, and we want pure sinusoidal current to be drawn from the AC source for reasons described earlier, because any harmonic is not really good. This power electronic converter, what we have learned so far, will contain diodes, inductors and capacitors. Among the circuits that we have learned, these three are the circuits that are popularly used in various applications. The center tap transformer rectifier, it's a 2 diode full wave single phase rectifier. It is used if the output voltage desired is typically in the range of 0 to 100 or maybe 200 volts, and usually a capacitor is connected at the output. So this is more popular, RC is more popular, and of course there is a compromise on the current drawn, but that is acceptable because the power levels and the voltage levels are fairly lower. When it is needed to generate a DC voltage of more than 200 volts, maybe from 200 to 320 or 300 volts in this range, because the peak value of AC voltage is 325, so we'll only get less than that. Even if you put a very large capacitor, we're going to get definitely less than 230 root 2. So in the range of 200 to 300 volts, this single phase bridge rectifier is used. One good thing about the center tap transformer is that it also does the job of stepping down the voltage, and further there are only 2 diodes, so causing only one diode drop in any given instant. Once the voltage desirable is more than 300 volts, greater than 300 volts, and in fact about 400 to 600 volts in that range, like 400 to 600 volts, one needs to go for a 3-phase rectifier, because that is not possible to achieve with a single phase supply. And again in 3-phase case, the output case, we have L filter possible or C filter which is possible, but if you use L filter, the output voltage will be limited to 3 root 3 Vm by pi, whereas if you use a capacitor filter, you can go up to more DC output voltage, but the current will have huge peaks like this. The input current will have huge peaks like this. To solve this problem of peaky currents drawn by capacitive filter, often an inductor is also added on the DC link. So we have an LC filter at the output, and of course R is the load resistance. So that will smoothen the current waveform drawn on the input side. However, it is still not a sinusoidal current. To achieve more sinusoidal current in certain applications, for example like UPS, uninterruptible power supply applications, another DC to DC converter is added after a diode bridge rectifier. So the input is single phase AC, we have a diode bridge, and after the diode bridge there is a DC-DC converter. DC-DC converters are typically made of fully controlled switches. The switches can be turned on or off at any time irrespective of the circuit conditions, and inductors and capacitors. So these elements go into a DC-DC converter, and the switches in these DC-DC converters can be turned on and off appropriately based on some control objective that needs to be achieved. in this application, if the switches of this DC-DC converter are switched, that means turned on and off, in such a way that the current drawn by the DC-DC converter looks like this, then automatically the current drawn on the input side will be sinusoid. The AC source current will be sinusoidal. Such current can be realized by appropriate control, and this is known as popularly PFC circuit, power factor correction circuit. A diode bridge with a power factor correction circuit, which will make sure that unity power factor current is drawn from the AC source. Additionally, a PFC circuit can also regulate the output voltage to be almost DC. So both objectives can be achieved. Output voltage being purely DC, almost DC, and input current being almost sinusoidal can be achieved by appropriately controlling this DC-DC converter. Another possibility is something called active rectifier. Active rectifier, which is shown here, it is a simple bridge circuit with 4 fully controlled switches, and these switches are controlled in such a way that the input current is sinusoidal and the output voltage is purely DC. When one wants to create a few thousand volts of DC voltage, a few thousand volts, something called multi-pulse diode rectifiers are used. We have seen diode rectifiers up to 6 pulse. There are 12 pulse rectifiers, 18 pulse rectifiers, 24 pulse rectifiers, and 36 pulse rectifiers. The basic idea behind all these rectifiers is to create multiple voltage sources of variable phase difference. See, with 3 voltage sources with 120 degrees phase difference, we were able to achieve a 6 pulse operation. If we have 6 different voltage sources that can be created, each is having 60 degrees of phase difference, then a 12 pulse operation can be achieved. Similarly, if you have different sources even spaced at even finer phase angles, then more pulse number operation is possible, and as the pulse number increases, the output voltage becomes almost constant even without a capacitor. And there is also an advantage in terms of input current. For example, the 12 pulse rectifier shown here will have an input voltage waveform like this IR. IR is this current waveform drawn in one phase. And how is this achieved? This is achieved by having a transformer with 2 secondary windings. One is connected in star, the other is connected in delta, and the star winding is connected to a 3-phase diode bridge rectifier, and also the delta winding is connected to a 3-phase diode bridge rectifier, and both of them are connected in series. So you have a 12 pulse output voltage waveform and also an input current waveform with little lower THD. THD of roughly 15% can be achieved in this case. As the pulse number increases, better and better THDs, lower and lower THDs can be achieved. However, when you need to generate voltages only within 1000 volts, like for example you want to generate a voltage of maybe 400 volts DC or 300 volt DC and or 600 volt DC, but still you want to draw sinusoidal current from AC source, PFC and active rectifier are the most popular solutions followed, and to realize these rectifiers we need fully controlled switches. It is essential to learn about fully controlled switches not just from the perspective of DC-DC converters or DC to AC inverters. It is also needed to realize an ideal rectifier, so that is why we will be discussing fully controlled switches in the next module.